Hey guys, and welcome back to another episode of Physics in 5, and today this is sort of the starting point of the Physics in 5 series. You can imagine it as sort of the base plate that we need to know to build up on. What we're doing today? Well, today we're looking at how we take measurements and how we measure those measurements. Specifically, we're looking at units and how we quantify the numbers that we get. So let's go. Okay, so let's take a look at what the first type of measurement. There are two. The first type is something I'm sure that many of you will have done hundreds and thousands of times, and it's called a direct measurement. A direct measurement is as easy as it sounds. It is something that you measure in the moment. So here we've got a little example of a situation. So we've got a car travelling down a road at some speed that we're trying to find. So the first type of measurement we make is called a direct measurement, and that is something that we physically measure ourselves. This might be the distance that the car travels, it might be the time in which the car travels that distance, it might be the mass of an object, it could be the temperature of an object, it could be anything, right? As long as it's something that you measure yourself, then it's a direct measurement. The second type is called an indirect measurement. Now this would be the speed in this case, because to get the speed here we divide the distance by the time, and that might be the same thing as getting the weight of something instead of the mass of something, which is a very common mistake that people make actually, is that weight is actually the force proportional to your mass. So when you get on a scale you actually measure your mass, you don't measure your weight. Weight is a force in a gravitational field. But yeah, the indirect measurement is something that is calculated. So how do we quantify a measure? And that means how do we give some meaning to a number that we obtain? Because if I say to you the number 13, that means absolutely nothing. But if I say 13 bananas, or perhaps 13 meters, or 13 degrees, then that gives it some sort of meaning to a number. And that's called a unit. And there are many units that people use to measure. In fact, anything can be a unit as long as it's a quantifiable object. So, and many of you may have heard of the empirical system versus the metric system, and those different units that we use. Now, because of this difference in measurements from where they come from, there is a system called SI base units, which means the International System of Units. Why it's SI, no idea. That's just what it's called. And these are defined units of measurement. Before, you may have heard of people measuring things in inches and feet, and perhaps furlongs, or degrees centigrade, degrees Fahrenheit. How do you define? I mean, an inch is supposedly the size of your thumb from knuckle to the top. So how do you decide on universal measurements? Now there are 7 different types of SI units, and these are supposed to be universal measures for a certain thing. The first of which is the unit for length, which is, as probably many of you know, the meter. It's given this little symbol, the little m, and of course it measures length. The meter is defined as the length that light travels in a vacuum in 1 second. Now light travels at nearly 3 times 10 to the 8 meters per second. But light will always travel at that speed in a vacuum, so the meter is perfectly defined. That distance that light travels in a vacuum was measured out to a meter and is now kept as a metal bar of a meter length at the same temperature in many places all around the globe, and so all rulers are based off that distance. It means that we can have fractions of these units. So we can have centimeters, which means 1 part in 100. We can have millimeters, again 1 part in a million. We can have kilometers, which means 1,000 meters. So with that in mind, then we come on to the second SI unit, which is the unit for mass. Now this may seem a bit backwards, because I've just told you that meter is a standard unit and kilometer means 1,000 meters. So why on earth is the SI unit for mass kilograms? Kilogram is equal to the mass of 1 litre of water just at the point where ice melts into water. and that is equal to 1,000th of a cubic meter. The reason we don't call this a gram is because we measure things in terms of the really small and the really large. So what we do is we give the standard unit that we deal with on an everyday basis is kilograms. For example, a bag of sugar is equal to 1 kilogram, but if I told you, oh, that's 1,000 grams of sugar, that sounds like a lot. Equally, in terms of human mass, the average person weighs 65 to 80 kilograms. If I said to you, oh, how much do you weigh, and you turn around to me and say, oh, I weigh 65,000 grams, that sounds like a lot. So in terms of the everyday objects, it would sound ridiculous if we measured in grams, which is why we use kilograms. Okay, now on to another very common one, which is the unit for time. And this is measured in seconds, as I'm sure you're well aware. There's really no other method of measuring time that we have at all, going back through history. And it's given the symbol S, small s, for seconds. A second is measured by a certain given number of transitions inside of a cesium-133 atom at 0 Kelvin. And we're going to get on to Kelvin, but cesium is a very consistent decay rate, so the second is always maintained. And even to this day, there are still atomic clocks all over the world that maintain the same level of time each time. It works out quite nice in that way, because then we measure 60 seconds is a minute, 60 minutes is an hour, 24 hours is a day. And the reason that that's done is because 24 and 60 divide quite nicely into sort of 12s, 10s, 5s, 2s. So you can split up a clock face quite nicely. Equally, 24 and 60 both go into 360. And 360 is obviously the number of degrees around a clock. The ampere, or given the letter A, refers to the electric current through a circuit. An amp is defined as the current that, if maintained between two infinite length conductors separated by a meter, would produce a force between them of 2 times 10 to the minus 7 newtons. Now that sounds quite complicated, but as long as it is clearly defined, it can be an SI unit. Okay, so this one may surprise you a little bit, but the SI unit for temperature is not actually degrees Celsius. The actual unit is the Kelvin, given the capital letter K. The Kelvin scale and the Celsius scale are technically, they scale the same way, unlike the Fahrenheit and Celsius scale. Now, 1 degree Fahrenheit is 5/9 of a Celsius. Now, the reason the Fahrenheit scale is so popular in places such as America is because saying it's 80 degrees outside is a lot more exciting than saying, oh, it's 26 degrees outside. The Celsius scale is based on the fact that at 0 degrees Celsius, ice is just melting into water. So you have that crossover point of phase of water, which is a very stable element to base a unit on. The Kelvin scale, on the other hand, is more of a thermodynamic temperature scale, which means that it's based on the intermolecular workings of water. What that means is, at 0 degrees Kelvin, you have the triple point of water, which is the point at which ice, water, and water vapor can exist at the same time. This is actually quite easy to do, in a sense of 0 degrees Celsius is 273 degrees Kelvin. So 0 Kelvin, referred to as absolute zero, is minus 273 degrees Celsius. 0 degrees Celsius is actually 273.16 Kelvin, and as such 0 degrees Kelvin is minus 273.16 degrees Celsius. The difference for this is you can't get negative Kelvin temperatures, which is quite handy in thermodynamic equations whenever you're using temperature to measure a specific heat capacity, or if you're using it to measure how chemical reactions go on. You don't end up with a negative number unless energy flows away from the system. So now we get on to more of a chemistry SI unit, the mole. Now this is given as the amount of a substance. It's written mol, not to get confused between meters. The mol is defined as the amount of elementary entities inside 0.012 kilograms of carbon-12. And that sounds quite complicated, but carbon is the most abundant resource on the planet. We're all made out of carbon. every living thing is a carbon-based life form. Carbon is everywhere. And these elementary entities may be anything from atoms, molecules, ions, electrons, protons, neutrons, whatever, but the volume that they take up is called a mole. Now you might have heard of this last one. It's to do with luminous intensity, which is the intensity of light. Natural light mainly is what it's based on, but it's often used to reference torches. So we often hear 1,000 candle torches, and the candela is defined with the CD symbol, but it's defined as the luminous intensity in any given direction of a source of monochromatic light, which means all of the light is the same frequency and the same wavelength, and therefore exactly the same colour. There's no interference going on with different frequencies or whatever. And that frequency is given as 540 times 10 to the 12 Hertz, just a fairly standard frequency for visible light. And it has a radiant intensity of 1/683 watts per steradian. So the steradian is given as the square of the circle that would be left on the wall at a 1 radian angle from a natural light source. We're talking about the ratio of a square length calculated using a square length. So we have a square length divided by a square length, and that means that the units cancel. So that's why steradians tend to not be included in the list I showed earlier. As for the watts, in this case, watts are a calculated unit, so they're not generally given SI unit status on the table, but they are again an agreed unit for power. So guys, thank you very much for watching my Units and Measurements Physics in 5 video. I hope it really helped understand where all these units come from, how we take measurements. If it did, hit the subscribe button, it helps me out. You can follow me on Facebook, you can follow me on Twitter. I usually link the videos and the articles on the website, which is here, on there as well, and I tend to keep up to date more on Facebook. If there's something you don't understand, Facebook or the website is the best place to get in touch with me. Equally, you can leave me a comment at the bottom of the video, and I tend to get back, if not within an hour, on the same day. So that's enough for me guys, thanks very much for watching, and I'll see you next time.